All right, today we're going to talk about concavity. This is a brand new topic, so we're going to start with the basics. So let's start with our definition, and we're going to be talking about whether the graph of a function is either what we call concave up or concave down. That's what we mean by concavity. So here's the true mathematical definition of concavity, concave up and down. I'll put them both up here. A function is concave down at any point where if you draw the tangent line, remember we spent a lot of time earlier this year about finding tangent lines. If you draw the tangent line and it's above the graph, then we call that graph concave down. But if you draw the tangent line and it's below the graph, we call it concave up. So here's a very basic example of that. It's a kind of a graph, it's basically like a curve. And you can see how it goes kind of up and then down and back up, that almost sideways S shape. Well, the blue part is concave down because if you look closely, you can see I drew in some tangent lines for you there. Each of the tangent lines on the blue one, the line itself is above the graph. It brushes up against from the top. We call that concave down. Now, on the red side, that's concave up because the tangent lines are below the graph. That green point that's marked in between them is a very important point we'll get to in just a few minutes. But for now, let's really focus on concave up and concave down. So what we want to do, instead of the mathematical definition of continuity, let's talk about it more as a concept. So this is how I like to think of it. Think of your graph or a part of your graph like a bowl, like a salad bowl or a cereal bowl that you might eat out of. If the bowl is facing up, like if you look at that red shape there, if it's a bowl facing up, like you could actually pour cereal and milk into it and eat out of it, we call it concave up. It's like a bowl facing up. But if the bowl is flipped upside down, like the blue one, we call it concave down. And to me, that's how I always think of concavity. Again, it's not the mathematical definition, but that's the concept of concavity, is whether a graph is kind of like a bowl facing up or down. So what we're going to do to determine concavity is we're going to use the second derivative. So remember earlier this year we did multiple derivatives. We said, okay, usually when we find the derivative we find f prime of x. But you can also find f double prime or f triple prime, the second, third derivative. Well, we're going to use the second derivative to find concavity. It actually works exactly like the first derivative test. So basically, if you remember from last section, wherever the first derivative is positive, the graph is increasing. Wherever the first derivative is negative, the graph is decreasing. Well, we have a very similar relationship, but instead of increasing and decreasing, it's concave up and concave down. And it's the second derivative instead of the first. So wherever f double prime, the second derivative, is positive, you have that concave up or that bowl-shaped up graph. And wherever f double prime is negative, you get concave down, like the bowl is flipped over. So let's talk about that green point in the picture. That green point is called an inflection point. And that happens whenever a graph changes from concave up to down or down to up. It doesn't matter which one is which. And one thing to just kind of think about here, when we just finished doing the first derivative test, we found our critical values and we tested them and we said, okay, well maybe these two are minimums and this one's a maximum. Well, a lot of times we got critical values that were neither minimums or maximums. A lot of times those are inflection points. Not every time, but a lot. So let me draw you guys a quick picture of a graph here. Let's say we had a graph that looks like this. And I wanted to talk about where it's concave up and concave down. And I'm going to use the same colors that match from that picture I showed you before. I'm going to do blue for concave down. So basically right here, this part, and I'll color it in so you can see it really well, this part right here If you look at just the part I colored in blue, even though it's extended on one side, you can see it's kind of like an upside down bowl. So that's concave down. But right where I stopped, I'm going to mark a green point. There's an inflection point right there, because if you look to the right of that point, all of a sudden you have that bowl-shaped up right here. And it does actually continue on this one. So that's a little bit more like a regular graph instead of just the curve I showed you before, but you get the idea of how you're separating this into where, if I chop it into pieces, where am I seeing that bowl-shaped up, concave up, and where am I seeing the bowl-shaped down, concave down, and then right in between, right where it changes from one to the other, you get an inflection point. Okay, so here's the work for today. We're going to do the exact same thing we did last section, except we're going to use the second derivative instead of the first. So last section, we did the first derivative test to test for increasing and decreasing and to find minimums and maximums. Today, we are going to do the exact same thing, but with the second derivative, and instead of telling us where it's increasing and decreasing, it's going to tell us where it's concave up and concave down. And instead of telling us which points are minimums and maximums, it's going to tell us which points are inflection points. But the good news is it's the exact same work. Now, one little side note here, we don't call this the second derivative test. It seems confusing. You think, okay, I used the first derivative test. Now I'm doing the same thing with the second derivative, but it should be called the second derivative test. There's actually a different use for the second derivative that we call the second derivative test that you guys will see next year in AP Calc. But just so you know, that's not really the name of this. All right, so for our example, I'm actually going to mix the last two lessons into one. So this is going to be a very long problem. We're going to take this function, f of x equals x to the fourth minus 4x cubed, and first, we're going to do the first derivative test and find all the local minimums or maximums. Then, we're going to take the second derivative and do the exact same thing. And the reason I'm putting two examples in one is just so you can see that you're literally doing the same thing twice. So let's go ahead, even though this is not what's new for today, this is last lesson, let's use the first derivative test to find minimums and maximums. So what I would do first is find the first derivative, f prime. Now I gave you guys a nice easy function for this. It's just power rule. So if I multiply by 4 and lower the exponent by 1, I get 4x cubed. Minus, and then on my second term, if I multiply by 3, I get 12. Lower the exponent by 1, you get x squared. Okay, so I got my derivative. Nice, easy question. And let's find the critical values. So critical values are where that thing equals 0 or is undefined. I can tell just by looking at it that's never undefined. It doesn't have a denominator that can be 0. So let's just set it equal to 0 and solve. Let's just say 4x cubed minus 12x squared equals 0. And I think I'm going to solve it by factoring out common terms. I can factor out 4. I can factor out 4x squared. And what that's going to leave me with is x minus 3. So I get two critical values here. I get x equals 0 from the x squared that I factored out from right here. And I get x equals positive 3 from the x minus 3. So let's put those two on a number line. Here's my number line. Let's say 0 is here and 3 is here. And split up our number line like that. So now what I'm doing is I'm going back to the first derivative test. I'm going to pick numbers from each interval, one less than 0, one between 0 and 3, and one greater than 3. And I'm going to plug them into f prime of x. And I'm going to I don't need the answer. I just need to know whether it's positive or negative. And one thing I want to mention here, if you look at what we have, all of these right here, the blue and the green, that's all f prime of x, whether it's multiplied out or factored out or anything. And the reason I'm pointing that out is that you can find little shortcuts on these plus or minus tests. So for example, if you think of the factored version right here, I'll circle it. If I'm plugging in numbers for x, and all I'm checking is whether or not the answer is positive, I can ignore the 4x squared, because x squared is always positive. That's one of the rules. Anytime you square a number, it's positive. So this right here is always positive. So really, all I need to do is check that x minus 3. So you can save yourself a little bit of time. So like, let's say the first number I want to plug in is -1 to see what happens over in that left interval. I could plug -1 in here and here, multiply it all out, subtract, see what I get, and just check to see if I get a positive or negative number. Or what's the best way to do it is I could say the x squared is always positive. I'm going to ignore that, the 4x squared. So I'm just going to take my number, subtract 3, and see what I get. So if I'm taking -1, -1 minus 3 is -4. Okay, that's a negative. And now all of a sudden my work is much quicker. There aren't always shortcuts like that, but if you notice one, it can save you a little time. Let's say my next number is +1. I got to pick something between 0 and 3. So again, I'm just looking at x minus 3. 1 minus 3 is -2, so this is negative. And then let's say my next number is 4 or 5 or 10. Pick anything bigger than 3. So let's say we go with 4, and I go back and I go 4 minus 3 is 1. That's +1, so I'm going to put a plus there for positive. And again, that was much easier than plugging them in and saying, like, what is 4 times 4 cubed minus 12 times 4 squared? Is that positive or negative? You could have done it that way, but I noticed a shortcut and it saved me a little time. So basically what's happening is my graph, minus means decreasing, minus means still decreasing, and then plus means increasing. So what I think I have here, the 0 is not a minimum or a maximum because it went from decreasing to still decreasing. So what I'm going to do is I'm going to say I probably have a minimum at 3 comma something. When I say probably, I just want to plug 3 into the original question and make sure I actually get an answer. So let's do that. If I go back to my original problem and find not f prime but f of 3, I would have 3 to the 4th minus 4 times 3 cubed, and that would be, let's see, what is that, 81 minus 108, so it's going to be negative, let's see, negative 8, 19, negative 27. I think that's right. So we get a minimum at 3 comma negative 27. Now remember, that wasn't new for today. That was actually last lesson. What we're going to do now, though, the second part of this question says now, let's find the inflection points. Well, what we're going to do is the work you see on the board right now, I'm basically going to repeat it. I'm going to do the exact same work again, except instead of with the first derivative, I'm going to do it with the second derivative. So let's go ahead and do that. Here's a blank page for us to do that on. I've left the important information, my original function and f prime. And the first step for this question, we'll go ahead and do it first, is to find f double prime. Remember, f double prime just means the derivative of the derivative. So I'm going to take the derivative of f prime, and I'm going to do power rule again. So I multiply by 3, I get 12. Lower the power by 1, I get x squared. Minus, multiply by 2, I get 24. Lower the power by 1, I get x to the first power. All right, so my second derivative is 12x squared minus 24x. Let's go ahead and set it equal to 0 and solve. Remember, the work should be almost exactly what we just did. So I'm going to factor out common terms again. This time I can factor out a 12x, and that would leave me with x minus 2. So this time my critical numbers, although technically they're not called critical numbers, that's a first derivative thing, but my x values are going to be 0 again for that x I factored out, and positive 2 for the x minus 2. So let's do a number line again. This time, remember, this work is exactly what we just did. This time my key numbers are 0 and 2. That's what's splitting up into intervals. I don't have much of a shortcut here. So remember, I just showed you that shortcut. If you want to plug in here, that's fine. But see how this time it's not an x squared out front, it's an x. So basically, you don't have a shortcut here. You can't just say, oh, I'm just going to plug in the x minus 2. Because that 12x out front could be positive or negative. We don't know for sure. It's always positive this time. So let's say I'm going to plug in -1 first. You have two choices. You could go back here to the original function, the original f double prime, and plug in -1 there. Or you can still use what's circled in purple. You just have to remember to do both. So for example, if I was doing that, let's say I'm plugging in -1. So I go 12x, that would be -12. X minus 2, that would be -1 minus 2, that's -3. So I'm getting negative times negative, it's going to end up being positive here. And again, we don't care what the number is, we only care whether it's positive or negative. So what I was doing is I was taking my -1 and putting it here, and putting it here, and then just saying, and what am I getting? I got negative and negative, negative times negative is positive. Now let's do the same thing with a positive 1. If I put a positive 1 in there, 12 times 1 is 12, that's positive. 1 minus 2 is -1, that's negative. Positive times negative is negative. So it's negative in the middle interval. Then I need something from the right side, maybe I pick 5. 12 times 5, that's positive. 5 minus 2, that's 3, that's positive. Positive times positive is positive. So everything looks exactly like our first problem. The one difference starts here. This is not increasing and decreasing. So don't draw the arrows in. You know, don't draw, okay, it's increasing and then decreasing. That's not what we're testing here. In fact, I don't usually draw a picture at all for this one. If you really wanted to draw a picture, you maybe could do something like this. For all the pluses, show that it's concave up. And for all the minuses, show that it's concave down. Although, like I said, the picture doesn't really help you. The reason I draw the arrows on the first derivative test is it lets you see the minimums and maximums. The idea here is, and this is one thing that's actually a tiny bit easier about this than the first derivative test, we don't have to differentiate. We don't care whether it's changing from a plus to a minus or a minus to a plus. There's no difference like there was for a minimum and a maximum. These are just inflection points. So what I'm looking at right now, what it looks to me like, is I have inflection points at 0, something, because it's changing from a plus to a minus, and 2, something, because it's changing from a minus to a plus. Now, to fill in the somethings, we do the same thing we did. We go back to the original problem, f of x, and we just plug in that value. 0 is actually easy. If I plug in 0 for both of those x's, I get 0. Now for the second one, if I plug in the 2's, I would get 2 to the 4th power minus 4 times 2 cubed. And that would be 16 minus 8 times 4 is 32. That's going to be negative 16. And those are your two inflection points. So I told you from the beginning, this was a very long example because it was actually two problems. The first derivative test was one thing all by itself. And then what we did with the second derivative, remember it's not technically called the second derivative test, but we repeated the exact same work with the second derivative. Instead of giving us increasing and decreasing and minimums and maximums, it gives us concave up, concave down, and inflection points. All right, let me just finish up the video with a quick summary here. I like to show this. Basically, if you're talking about whether something is positive or negative, I went through, first of all, just f of x, which is our original function, and then both the first and second derivative. So this is a good summary here. F of x, our original function, for me to say it's positive or negative, I'm just talking about a function value. I'm talking about a point. So if I say f of x is positive, that means it's a positive y value. It's above the x-axis. And if I say f of x is negative, then it's below the x-axis. So basically, that's just where the point is on the graph. Now, the first and second derivatives are our last two lessons. So the first derivative, wherever it's positive, the graph is increasing, and wherever it's negative, the graph is decreasing. For the second derivative, wherever it's positive, the graph is concave up, like a bowl-shaped up, and wherever it's negative, the graph is concave down. And that's a summary of like our last week's worth of lessons, really all in one graphic here.